Section: Introduction. In this section, we examine the widespread inclusion of coding courses in university programs worldwide, highlighting the growing importance of programming skills in the digital age. The rise of advanced large language models, LLMs, like Codex, which powers GitHub Copilot, prompts us to reconsider how coding assessments are conducted in educational settings. While previous studies have focused on the coding capabilities of LLMs through benchmarks like MBPP and MathQA Python, our research centers on how AI may impact university coding courses. Instead of just assessing AI's ability to solve coding puzzles, as seen in other studies, we investigate how AI could influence a practical coding curriculum in a 10-week coding course within a physics program at Durham University. Physics degrees involve a diverse range of assessments, including lab experiments, presentations, written exams, essays, and coding tasks. This variety sets physics apart from other disciplines like mathematics, chemistry, English literature, and computer science, each with their own predominant forms of assessment. This diversity within physics offers a unique opportunity to explore AI's impact on different types of academic evaluations. While AI may not have a significant influence on hands-on lab work and presentations, its impact on essay-based assessments is becoming more pronounced as AI can now generate high-quality work comparable to that of humans. A crucial aspect of a physics degree is how students understand and apply core physics principles. Recent studies show that LLMs are improving in their comprehension of physics concepts, approaching human levels of performance. However, there are still some notable errors. This progress underscores the need to continuously assess the role and effectiveness of coding assignments as AI technologies advance. By focusing on physics coding courses, our study aims to evaluate the ongoing relevance, usefulness, and integrity of such assignments in accurately assessing student performance in a rapidly evolving technological landscape. To ensure transparency, the code used in our research is openly accessible on GitHub. Moving on to the methodology, our study aims to evaluate how well modern large language models, LLMs, can handle coding tasks typically assigned to university students, using a blinded marking approach to assess code written by both students and AI. In the context of physics, coding is primarily used for simulations and data analysis, emphasizing the creation of clear, well-labeled plots that explain the physics behind a scenario. This study contrasts with computer science scenarios where students need to justify their coding choices, focusing on readability and maintainability. To determine if ChatGPT is a suitable coding tool for physics education, we evaluated 14 plots against a specific marking scheme in a 16-page report, assessing both AI-generated and student-authored submissions. The coding assignments are from the Laboratory Skills and Electronics module at Durham University, involving essential laboratory practices, electronics, and coding tasks. The Python coding segment spans 10 weeks with weekly lectures and 8 assignments covering various topics like numerical methods and Monte Carlo simulations. We collected submissions from the student cohort and randomly selected 55 out of 103 participants for evaluation. Each assignment includes tasks graded automatically and manually, with a total of 14 plots produced throughout the course, contributing to the final coding mark. Section Summary. In this section, we explore the impact of advanced large language models, LLMs, like Codex on coding assessments in university courses, focusing on a 10-week physics coding course at Durham University. The study evaluates the effectiveness of AI in coding tasks traditionally assigned to students, particularly emphasizing the creation of clear, physics-based plots and the performance of the code used for simulations and data analysis. By comparing student and AI-generated code through a blinded marking approach, we aim to assess the validity and integrity of coding assignments in accurately evaluating student performance amidst rapid technological advancements. Section: Generating the AI code. In this section, we generated AI code for completing assignments on an online platform. To make sure the AI interacts correctly with the text, we had to convert the notebooks into a suitable format for the AI model. Without clear instructions, the AI might misunderstand the text and make errors like redefining variables. The assignments focused heavily on assert statements, which sometimes led to irrelevant information being evaluated. Even if the AI made errors in some parts, it shouldn't automatically receive a 0 score for the entire assignment. To ensure a fair comparison between AI-generated and student-generated work, we pre-processed the assignment notebooks before inputting them into the AI model. However, this pre-processing could potentially bias the results by assisting the AI too much. We only made necessary changes to help the AI complete the assignments consistently. Despite these efforts, there was still some unnecessary information in the inputs given to the AI. We then created a second set of inputs with additional enhancements to optimize the AI's responses, known as prompt engineering. We categorized the AI-generated work into 5 groups, including raw outputs from different AI models and a mixed category combining student and AI work. These categories were evaluated blindly by 3 markers, resulting in a total of 100 submissions. The scores from the markers showed that students achieved an average of 91.1%, while the best-performing AI category, GPT-4 with prompt engineering, scored 81.1%. A statistical analysis revealed that the AI, although impressive, still lagged behind students in physics coding assignments. Prompt engineering significantly improved the AI's performance, showing clear benefits. Interestingly, submissions combining student and AI work scored lower than AI-only submissions, possibly due to variability in the quality of student work sampled. Section Summary. In this section, we discuss the challenges encountered when generating AI code for physics assignments using LLMs. We highlight the importance of pre-processing assignment notebooks to align with AI capabilities and the impact of prompt engineering on improving AI performance. Our study reveals that while GPT-4 with prompt engineering achieved a score of 81.1%, it still falls short compared to the average score of 91.1% obtained by university students in physics coding assignments. Additionally, prompt engineering significantly enhanced the performance of both GPT-4 and GPT-3.5, emphasizing the benefits of tailored prompts for AI-generated work. Section: Author Identification. In this section, we evaluated the authorship of submissions by assigning scores on a Likert scale. The results are shown in figure. We found that genuine student submissions were more accurately identified as student-authored. By converting the Likert scale to a numerical range, we calculated average scores for different scenarios. For instance, GPT-3.5 with raw input had an average score of 0.033, while GPT-4 with prompt engineering had a score of 1.167. The mixed category, which includes both human and AI work, had an average score of 1.300, and solely human-created work scored 2.367 on average. Our analysis revealed that submissions with AI involvement tended to be categorized closer to definitely AI or probably AI on the scale. We conducted a Cochrane-Armitage test, which showed a statistically significant trend indicating that as we move from definitely AI to definitely human on the scale, the proportion of human-authored submissions increases. When reviewers categorized the Likert scale responses into AI or human, they achieved an average accuracy rate of 85.3%. The content generated by the more advanced GPT-4 model was found to be closer to human-created content, especially when prompt engineering techniques were applied. This is illustrated in figure, which demonstrates that human-generated content is generally of higher quality than AI-generated content. Our study suggests that while the most sophisticated AI models may not yet match human expertise in university-level physics coding assignments, there is a clear improvement from GPT-3.5 to GPT-4. This improvement aligns with findings in other fields, indicating a continuous advancement in AI capabilities. Educators should consider integrating AI into educational practices, such as through pair programming tools like GitHub Copilot, to enhance coding education. The lower performance of AI in raw input categories suggests that students are likely to benefit more from completing assignments themselves. However, The extensive prompt engineering required for other AI categories raises concerns about academic integrity. Implementing barriers to make the pre-processing more challenging than the assignments themselves could be a potential solution. Our findings show that markers were able to successfully identify AI-generated work in coding assignments. Evaluators noted differences in design choices between student work and AI-generated content, with students often making more creative decisions. These observations highlight the unique aspects of student work that differentiate it from AI-generated content. Section Summary. In this section, we analyze the authorship scores assigned to submissions by evaluators using a Likert scale, showing that genuine student submissions were more accurately recognized as student-authored. By converting Likert scale values to a numerical range, we found that content with AI contributions tended to be categorized closer to definitely AI or probably AI, with GPT-4 models showing improvement over GPT-3.5, especially when prompt engineering techniques were applied. This study suggests that while AI models like GPT-4 are advancing, human-created content still tends to be of higher quality, with markers successfully distinguishing AI-generated work based on subtle design differences and plot characteristics. Section: Limitations. In this section, we address the limitations of our study. We focused on how the pre-processing steps impacted the quality of the AI's output. Even though we kept the pre-processing minimal, it was crucial for getting the AI ready to understand and perform tasks effectively. Through prompt engineering techniques, we saw a significant improvement in the AI's performance, backed by statistical evidence. Exploring more advanced prompt engineering, like providing detailed instructions, could further enhance the effectiveness of the AI model. However, this approach shifts the evaluation focus from the AI's inherent capabilities to how well humans interact with the AI. Previous research, such as the work by Ghassemi et al., has demonstrated that user involvement can greatly influence the performance improvements seen with AI, adding another layer of complexity to any analysis.